Good day to all of you. We shall continue with our discussion on design of controllers, specifically for DC-DC converters. As you recall, we have done the modeling of the DC-DC converters, and in last few classes we have been discussing the basic principles of the controller, reviewing them in fact, and trying to understand the operations of the PID components of a controller. The PID controller is one of the most robust controllers and very popular in the industry too. And that is what we would be using for ultimately to close the loop for the DC-DC converter too. So, in the last class we had discussed, we had completed our discussion on the PID components and had just begun to look at how the P, I and D components can be implemented using op-amp. So, we had started with the integrator, and then we shall continue on towards the other components and see how we can integrate it with op-amps. Of course, if you are using a digital controller, if you are using a digital processor like a microcontroller, then you have to implement the equations, the PID equations within them. So, coming to our topic here of implementing the controller, let me again bring you back to our block diagram. You may be already knowing this block diagram, but let us write it down once again. We have K I, the integrator portion. The integrator, I am going to write it as 1 by S. You have the K P portion, the proportional gain, and you have K D, the scaling for the differentiator, and I am going to write the differentiator as S. And the denominator, I am going to write it in dotted on another color as S plus A, implying that you cannot escape S plus A, even though S is the only thing that is required. So, S plus A is a pole which is very far in the frequency axis. And all these outputs are added up in this fashion. Plus, plus and plus, and the output of this goes to pulse width modulator. We will call that one as pulse width modulator PWM, and the output of that goes as the control input D to the DC-DC converter. This is the plant. The sensed output could be V naught, is fed back and this is, let us say, V naught reference, V feedback, V naught feedback. or just V naught, so that you have less number of subscript to worry about. So, we had in the last class mentioned that this is the reference, it could be any reference, it could be current reference, voltage reference, depends upon what you actually want to control, Now, let us say for example, that we want to control the output voltage of the DC-DC converter. So, that is the one which is fed back, and a suitable reference for that is the one which we need to apply the desired reference. Now, this is our control structure. In brief, there are still a lot of details that we need to worry about, which we will do that as we progress. We had been trying to replace these blocks. We have been trying to replace these blocks with op amps. So, first what we did was that in the last class, we replaced the comparator portion with an op amp, a differential op amp. Let us say this is the plus and this is the minus. So, a diff amp is written in this form. You can refer to any book on op amps, and you can get a host of op amp circuit ideas from them. So, this is the positive is connected there, the negative is connected to V naught. So, what we shall do is connect it in this fashion. Now, all these resistances are for now, let us maintain it as same values. So, you will get an error E, which is nothing but V naught ref minus V naught. This E equals V naught ref minus V naught into R by R, but as the values of resistance are all equal, they actually cancel out and this would go. So, it is just V naught ref minus V naught. Okay. So, this is the first part, comparison. I am going to remove this so that we do not clutter up the board. And next, we had replaced the integrator portion with op amps. So, let me do that for you now. Recall, go back to the circuit that we discussed in the last class. It involves two op amps, one for integrating and another for setting the gain. But you can reduce the number of op amps, but right now do not bother too much about the number of op amps. We shall just try to replace the equations with op amps. So, this is an integrator. Let us say this is R I C I. You can add one more gain stage here if needed, and that is what we had included in the last class, minus and plus. So, this RI1 and RI2 would give not only gain, but also the inversion. This portion gives additional gain plus inversion. Okay. So, you have 2 degrees basically setting the gain of this stage and setting the integration gain of this stage. You have an inversion here, you have one more inversion here. So, from here to here there is no inversion. Or you could remove this stage and just set the gain, integrator gain, by choosing properly the value of this and this. So, let us probably make things simpler. For now, let me remove this stage, one set of reduction. So, we have it like this. What is the output here? You have E as the input, you have E as the input here, and let me call it as the integrator V naught I, output of the integrator. So, V naught I is, now there is an inversion, we will keep it as minus 1 by R I C I integral of E dt. This is the equation of the integrator output. So, this essentially is the gain K I and the integration E. So, this would be your K I in your. So, properly choose R I C I product to achieve the value of the desired gain scaling. So, let me again wipe out this portion so that we do not clutter the board and look at the next portion. The next portion of course is K P. Remember that we now have an inversion at this point. We will take care of this inversion while doing the summing. Okay. So, we will give inversion to all these and then take care by giving a summing point at the summing point. Now, this portion, the proportional or the gain portion, can be addressed by putting one single op amp here. We can introduce an op amp here, minus, plus, and gain. This is an inverting amplifier, recall from your op amp classes. So, if this is RF and RP, we have the input as E here and output as V naught proportional. And what is V naught proportional? V naught proportional equals minus, there is an inversion, RF by RP, that is the gain, into E, the input. This portion is the proportional gain K P that we have been using till now. So, that is the implementation of the proportional part in using op amps. Notice the change of sign inversion there, we are using an inverting amplifier. And let me again erase this portion to clear up the board. And let us see what we need to do for the next component, which is the derivative component. So, let us erase this part and include another op amp. Let me use the minus and plus inputs. Now, look at the integrator. The integrator is having R here and C there. We just have to interchange that. We put the C on the input side and use R for the feedback portion. So, you have C, D, R, D. All the op amps have power supply pins, power supply inputs. So, you should not forget that. Now, the output of the differentiator is given to the summing. Now, the input to the differentiator again is E, and at this point you have V naught of the differentiator, output of the differentiator. So, what is the transfer function of this? Look at, if you look at the Laplace domain, V naught d s by E of s equals R of d by 1 by s c d. This is so 1 by s c d, which is nothing but s c d r d. So, apparently, here you see that the transfer function appears ideal, where you have an ideal s and a scalar c d r d. However, understand that you are using a practical op amp, the practical components. Op amp has a pole very far in the frequency domain, very far on the frequency axis. It is nothing but a low pass filter. So, this will introduce that high frequency pole, the op amp. Op amp is a low pass filter. That op amp's pole will be the high frequency pole, which actually is implicit and it is there. You do not write it, but it is there. Remember that it is never ideal. Okay. So, we shall clear out this portion of the board and keep the rest. C D and yeah. So, you have the outputs from the integrator, from the proportional part and the derivative part. Outputs of all these need to be summed up. So, let us do that summing again using one more op amp. So, this portion we shall try to remove and replace it with a summing op amp. So, this is removed. And let us incorporate an op amp here. So, these are ground points, these are ground points, so on. Now, let us erase these, make some space for some resistance. Okay. So, let us put the summing resistances here. So, we have 3 summing resistances and the output of that. So, let us say for simplicity, we keep all these resistances R. So, this feedback R divided by this R will be the gain for this I stage. This feedback R divided by this R would be the gain for the proportional stage, and so on, and all will be summed up. Now, let us connect them. So, to one end of the summing R, you connect the integrator output, then to the another R, you connect the proportional controller part output, and then to another R, you connect the differential output part. You see that you can further have control on the gains for each of these parts by having a control on these values of the resistances. So, let us give different names for that. For these resistances, so it would be, let us say, R summing I, or summing P, or summing D. So, the gain for V naught I, so what will be at this point? This is an inverting which will further invert this. So, therefore, from here to here there is no inversion. Okay. So, at this point we have V c. So, what is V c? I shall write it below here. V c equals V naught I, it goes through this gain R by R S I, then adds up V naught P R by R S P plus V naught D into R by R S D, each individually scaled. Now, all these sum together and there is an inversion. Do not forget that, this inversion. Again, I am going to remove this clutter. So, you have 1, 2, 3, 4, 5 op amps. So, this 5 op amps together are basically implementing your PID block. The input comparator, the error is the output of that, which goes through each of these I, P and D blocks. Output of them are summed up to give you Vc or the control voltage, which goes to the PWM and then gets converted into time and then goes as input to the DC-DC converter. Now, this PID block is not complete if you do not include the anti wind up. When the value of Vc goes beyond a particular threshold, what do we want to do? We do not want the integrator to integrate, or we want to just stop the stop the capacitance from accumulating any further charge. So, you just clamp it. So, how does one do the clamping? It is by putting, let me create some space. So, you can implement it by putting 2 Zeners back to back like this. So, let us say you want to set the threshold at around 3 volts, you need to use 3 volt Zeners. You want to set the threshold at 5 volts, you need to use 5 volt Zeners. So, these Zeners, one for the positive direction, another for the negative direction, because you do not know what is the direction of the error, and will act as the anti wind up clamp. Okay. Now, this is a circuit that we developed from the block diagram as such. There was no reduction in the number of op amps, but this is a rather unwieldy circuit. You can do lots to reduce the number of op amps and keep things simple. So, let us try to improve this circuit. First and foremost, you can try to see if your controller can be restricted to just P and I, meaning if this is your omega axis and this is your gain in dB, and let us say your plant has a low pass characteristic like this, keeps going down, and to this low pass characteristic we have the controller. Controller is trying to pull up here. So, the controller, the integrator portion tries to pull up here, then the proportional portion is trying to maintain it at this point, let us say. And because it is not changing with frequency, and the differential portion is trying to pull up the gain at much higher frequency. So, if it does not make much difference in the bandwidth, if the system is already slower, then it makes good sense not to have the derivative, just to have the proportional, the integrator portion I, and after some point the P proportional portion. After some point, actually that is where the D portion comes in, because these are noise sensitive zones. It is always good to see avoid the D in the first iteration. If your system works well with just P and I, then stop with it, do not go further to include the D. Only when your dynamics are not really up to the mark and you really want to improve the dynamics, you try to put in the D. Most of the controller will just have this, the P and the I part, and therefore, you have what is called the PI controllers. So, the PI controllers are the ones which are most popular, and most of the plants seem to be okay with just PI controller. They suffice and meet the specifications. Include the D part only if absolutely necessary. So, if we look at this system plant, let me copy this portion and shift it to another page here. And let us erase the derivative part. We do not want the derivative part. For most of the controllers, it is okay to do away with the derivative part. Just the PI is sufficient, like that. So, this would be a PI controller. So, we have reduced one op amp, of course, with the reduction in the feature, that is the D component. Now, look at these two parts, look at these two parts. What is the transfer function? The transfer function of VC is nothing but V naught I, and to keep things simple, let us keep these R value gains, the summing gains unity, so that we can just say that plus VOP, and which is nothing but, and I shall assume that we are going to put this anti-clamp diodes always, but I want to clear up some space to include. So, you have 1 by RICI integral of EDT plus RF by RP E. This is nothing but, if I say this is Ki by S plus RF by RP, then this becomes ES, ES, VCS. So, the transfer function is nothing but VCS by ES, the error, which is nothing but Ki by S plus RF by RP. So, this is the transfer function of this I and P block. Now, can we replace it with a single op amp having similar transfer function? So, if we are able to do that, then we can eliminate many of these op amps and make the circuit simpler. So, let us check if we can do something like this. So, we have an op amp, and to the op amp the input is E like before, and let us say this is called R1, R2, and this is C1. Now, let us try to find the transfer function of this new op amp circuit VCS by E of S, that is from the output to the input. So, in this S domain, this is nothing but R1 plus 1 by S C1 divide by R2. There is an inversion here. So, taking in the inversions also into the gain, this is a portion which is like R 1 by R 2 plus 1 by R 2 C 1 to 1 by S. So, this is your K P plus let us say K I, or if you take out the inversion, like here we have not included the inversion, this is understood to be there, and then you can keep it separately with the input. Then you see that this is of a form, this gives a transfer function of a form similar to the earlier circuit. This is K I by S. And this portion is similar to this portion. And therefore, we can as well use this circuit. Let me clear up this. Yeah, because this gives exactly the same kind of output as this, except here there is no inversion. In the earlier case, there is an inversion with this op amp, and then followed by a summing op amp which provides an inversion. So, there is an inversion here and an inversion here, leading to a double inversion, therefore positive. Now, in the case of this single op amp, this is a single op amp which gives an inverted output. So, there is just an inversion here, which means this is going to be negative. So, you can introduce one more inversion anywhere, either within this block or here. So, if you give an inversion here, it would mean that we interchange this to that and this to that here. So, we have an inversion here which is now minus V naught ref minus V naught. So, this inversion followed by an inversion here, followed by an inversion here, would again reach here with no inversion, and the phase would be in proper context. So, be careful about the inversions. Whenever you do changes in the circuit, keep track of the number of inversions, or like as we will later on do in a practical case, if you have lost count of the number of inversions, we shall, when we do the online tuning, first check whether the phase relationships are okay end to end, and then do the closing of the loop. Okay. We will get to that later, but right now try to keep an account on the number of inversions. Now, we could further reduce the controller if you want to. Of course, here do not forget that we shall always put 2 diodes, Zeners back to back to take care of the anti wind up. These are the anti wind up clamps. Now, if you observe, can we do something such that these two op amps can be combined together and made into one single op amp? This is nothing but a difference amplifier, and this is nothing but an inverting amplifier with impedance gain, a gain which varies with frequency, not a resistive gain. So, if we look at these two resistances, convert them to impedances of this type both here, then they become a difference amplifier, and additionally they can also do the integration. So, let us have a look at whether we could do something like that. Now, if we replace this by this here, one should arrive at a single op amp solution, but however, this is not a very good implementational strategy. First of all, you need to have a resistance across to provide a bias current path, okay, which will introduce a low pass filter and change the equations a bit. So, it is better to not do an oversimplification and have everything on with just a single op amp. It is easy also for you to debug to keep the earlier 2 op amp structure. Let us go to the earlier 2 op amp structure like this, so that it is clear and easy for debugging and separately tuning. Otherwise, even the equations become very complicated, and trying to adjust one value of a resistance would affect not only Ki, but it may affect Kp also and Kd also, and therefore, the decoupling is lost. So, it is preferred that you just keep it in this structure as shown here. Now, this is the circuit implementation part of the PID controller. Keep this in mind, because you will try to if you want to implement it with a DC-DC converter, you need to remember and reconstruct them in this form. Now, here there is one black box, which is this, the PWM, which we have not discussed so far, implementing it with op amps. So, we shall also discuss that gradually and see how we implement it with op amps. So, but for now, coming back to this PI controller, we now know how to implement the various parts or blocks of the controller. Now, we can put it as one single PID block, knowing fully well that they contain op amps. This also contains op amps, and the output of that goes to a PWM block, and the output of that goes to the controller, the plant, which acts as the input to the plant, the D input to the plant. The output from the plant, Y or V naught, sensed output. Always remember that there is a power input and a power output. You are actually controlling the flow of power from here to here. This is from V in to V naught. Do not forget that. And that V naught which is sensed, from there through an opto isolator or through a Hall sensor or through resistive division, that sensed output is fed back here. We will see about how we do the sensing and feedback also later. Now, we have this V naught reference and V naught, we have error. Output of the PID controller VC is the PWM. Now, in the case of the DC-DC converter, we are doing the modeling which is small signal. But all the signals that you get here are having two parts. So, let me say it is having steady state part plus a V naught hat. Now, this reference is something which is set by you. So, this is having a steady state reference part plus small signal deviation is 0. So, the hat part is 0. Then here the D is having a steady state D plus a D hat part. Now, coming to the input of the PWM, likewise VC equals a steady state VC part plus a VC hat part. So, let us do a minor modification here in the control structure. Let us say that at this point we have a summer. This is a summer. So, we are going to insert here a term, a feed forward term, which is based on the steady state part. So, let us say I am going to insert VC here. steady state portion of the VC, which means here what will be coming in would be VC hat. So that at this point it is VC plus VC hat. Now, in this comparator, when you subtract this and this, that is, you have V naught ref plus 0, steady state part plus 0, minus again a steady state part plus V naught hat is your error. Now, that can be written as V naught ref minus the steady state part minus, or let us say plus 0 minus V naught hat. This is the small signal part of the error. Now, in the steady state, because we are using PID integrator, this will tend to 0. So, this is not there. So, this portion, because you are using a PID controller, will become 0, and we know that it is 0. We need to take care of the deviation, only the deviations. Then the PID can focus only on the deviation, and the steady state portion can come directly from the reference. If you say you have a V naught requirement of this particular thing, a value here can be given as a feed forward item. Let us say we put in a block there. And this block goes in, and it takes the value from there, or much better, it can take the value from here, and also by measuring the input. All from the steady state model. So, how we design this block and how we take the inputs, various inputs, and from the reference, and then try to arrive at the value of VC, we definitely will see that later. But remember that we can separate into the steady state portion. So, the steady state portion can be addressed and taken care of by the feed forward terms. The feed forward terms can be added either at this place or after the PWM appropriately. You will get to understand the context and the nature, and by which way we will be adding once we know all the circuits put together. If we allow the PID or the controller portion to take care of only the small signal terms, then they will respond much faster, the dynamics will be much faster. However, you could allow the PID to take care of the entire signal, both steady state plus small signal too. So, both are okay, but only thing is that the dynamics will be slower. So, this is the structures, and you can improve upon these structures. You can get many structures, control structures. The simplest of course is to just allow the structure to be in this form. And allow the PID controller to take care of everything. Of course, with the constraint that it will be slower, the dynamics will be slower. Still, that does not matter. We have today seen how this looks like with op amps. In the next class, we will see how this looks like. Okay. And then we will have a picture of every component in our minds, and then we can integrate all of them along with the DC-DC converter here and try to make the closed loop operation possible for the complete integrated system. So, that is how we will progress. Okay. Thank you for now.